So first of all, thank you very much for coming. So today's speaker is Sigmund Kohler. He comes from the Institute of Science, Material Science in Madrid. Okay, yeah, which is just a quick translation. Okay, so okay, let me introduce him very briefly. So he studied physics at the University of Ulm, and then he got his PhD in the group of Peter Hangi in the University of Augsburg, which probably is familiar to many of you. Then he got a postdoc in Madrid, actually, in the Universidad Autónoma de Madrid, in the group of Nanoscale. And after that, he moved back to Germany, to Augsburg. And then he spent quite a few years, 8 years, where he got his habilitation. Then he became, let's say, a researcher and professor in that university. And last year he got a Romanica position in this institute in Madrid. And very recently he became permanent as a Científico titular, is the name for these positions. Okay, so he will talk about Ratchet currents in nanoscale conductors.
Okay, thanks Madrid a lot for the kind invitation and the nice introduction. I'm actually happy to be here. It's quite a nice institute, and also to speak in front of a relatively big audience, I like also a lot. And well, today I'm going to speak about a project that I actually started when I moved from Madrid back to Augsburg and started towards my habilitation track in the group of Peter Hangi. And one long-term project was to study mesoscopic conductors in electromagnetic fields, in AC fields. And as at least those who are a bit familiar with the field can imagine, there are well, many effects, and one, the probably most famous effect in these kind of systems, in driven systems, is the Ratchet effect. And today I will focus a bit on the results that have some relation with the Ratchet effect, because as far as I know, many of, or at least some of you are interested in that topic. Well, the sketch here already tells a bit about the systems that we are considering. These are what is called molecular wires. They were quite fancy some, well, 7-8 years ago. Now the field calmed down a little. Maybe it's also due to the advent of graphene, where many researchers left the field and are now working on graphene. That was our original motivation. But unfortunately, it turned out that the experiments in molecules, they are extremely difficult, and so we finally found more interest from researchers that are studying quantum dots. I explained in short a little about the systems, about the experimental background. So our original motivation were essentially these experiments done around the year 2000, where it was possible to contact single molecules with gold tips and to drive a current through them. And probably first, although maybe not so clean experiment, or not so good resolved experiment, was the one in the group of Madrid. But it was by now 12 or 13 years ago, the first experiment of that kind. Later on, there were also other experiments here. This was at least so far, I think, still the only experiment that was done in Germany. It's always, I mean, much better visible here in the sketch. We have gold tips and we have some molecules that are made of benzene rings in between. And if you apply a voltage to the gold contacts, then a current will flow. And essentially, these are very small currents, rather tunnel currents than way below the conductance quantum. And there were also other experiments like this here, where they measured the current through a bunch of molecules. So usually the bunch of molecules consisted of just a few, say 3, 4, 5, and if you scale all these currents, which are shown as a function of the bias voltage, then they fall back to one curve. So we have 1, 2, 3, 4, and 5 molecules contacted. Now, say the natural thing that one likes to do in an experiment, if one, I mean, molecular physics is dominated in one sense by excitations, coherent excitations with light. And of course, the natural idea is to do the same now with conducting molecules, but actually the setup in an AFM picture looks like here. So we have what is called a break junction, which is essentially some metal that is well, literally broken, so a small gap opens, and in the gap there is a molecule. So you can imagine, I mean, this is on the more or less micrometer scale, that the gap, which is on the angstrom scale, is much, much smaller. So the large fraction of the experiment, of the setup, is pure metal, and here only in a very small gap there are the molecules. And if one now tries to excite such a setup, for example with a laser or with coherent light, then of course one sees all kinds of effects, like, well, most of them are due to thermal heating, but these are not really clean molecular excitations as one likes to observe. So it turned out that it's actually much, much more difficult than I guessed originally. But there are also some ways to circumvent these difficulties, and the probably most promising setup is the one proposed by Joachim Ratchet from the Technical University of Munich. And what they are doing, they propose to make the whole setup part of a so-called SNOM, scanning near field optical microscope. And the essential idea of the SNOM is that one has a sort of chip which is made of glass, and through the glass one can of course conduct light. And if the tip is coated with, for example, gold, then the whole setup has, well, something that in principle emerges like a problem, but for the present purpose it actually opens some nice, or gives some nice options to use that effect, which is at the edge of such a glass tip, the coating is never perfect. So there is a kind of gap in the gold surface, and through that gap, light can can leave. So for a molecule which is contacted here at the tip, the light can be focused quite well on the molecule. So that opens some way to excite just the molecule and not the whole setup. So in that way, thermal effects can be ruled out, at least to some extent. And there's actually a second effect of that tip, which is the so-called surface or tip-enhanced Raman scattering, as it is known from other fields. And that means that here at the corner of such an edge, the electric field is usually much enhanced, just due to classical electrostatic effects. And that means that finally, with a relatively moderate amount of light, one can create relatively high field strengths here at the tip. So that's a promising setup for observing all these effects that I'm going to talk about also with real molecules. But say the traditional experiments are with so-called artificial molecules. Artificial molecules or artificial atoms, which were made first, are what is also called quantum dots. A quantum dot is in a two-dimensional electron gas, a constriction which is so small that the electronic structure of electrons, or the structure of the energetic spectral properties of the electrons in that structure, they are like in a molecule, or like in an atom. So in particular, these have discrete energy levels. Unlike in a normal bulk material where the energies are continuous, in a quantum dot they are discrete. So we essentially have here this constricting area in the sub-micrometer regime, and if one puts all the numbers, one will find that the electron levels, also for practical purposes, they are really discrete. So it's pretty much like an atom. And if you couple atoms, you end up with molecules, and that's why these coupled quantum dots are called artificial atoms. Now in a solid state setup, one can of course contact such molecules or quantum dots with leads, which means we have here some area which is relatively large, so it really forms a continuum. So we have here, well, more or less to a good approximation, we have a Fermi sea. So we have electron reservoirs at a source and at a drain, and if we apply a voltage, then the Fermi level of the source is higher than the Fermi level of the drain. We have some discrete levels in between, and we can now ask ourselves how the current flows through these discrete levels. So that's already a very classical experiment, and by now people are able to do that much better. I mean, this experiment is one of the first experiments with two coupled quantum dots, and it took almost 10 years to make the system bigger, to add a further quantum dot, so to have triple quantum dots. So this was experimentally quite a big step. Now these systems, they are relatively flexible, which means they can be tuned. For example, if one applies a gate voltage to one of these pins, one can shift up and down these levels. And if you look at the current as a function of that gate voltage, you will find that first, without any radiation, you will find a peak at a certain value. And that peak is physically corresponds to the alignment of the two quantum dots, or of the levels of the two quantum dots, so that resonant tunneling is possible. And resonant tunneling is always much more probable than off-resonant tunneling, and that enhances the current, so that explains the current peak here. Now if one does exactly the same in the presence of microwaves, one finds also these side peaks. And these side peaks, they correspond to resonant transitions of an electron here in the lower level to an electron in the upper level. And also the de-excitation has the same probability, so this also happens. And finally, they found this picture of this, what is called photon-assisted tunneling. Now, from a theoretical point of view, there are a couple of interesting questions that one can address. The first one is probably what one wants to see in an experiment first, which is how does the conduction, or do the conduction properties change under excitations with lasers, or in the context of quantum dots with microwaves. And the second question that we asked ourselves in the very beginning, can one observe ratchet or pump effects in such setups? And actually, that will be the focus of today's talk. Another thing is, can one control the current by laser fields? And another big issue that we studied a lot was how are the noise properties of the current? So how does the shock noise change once we excite the system with lasers or microwaves? And well, so with this motivation, we studied this kind of models. Well, for quantum dots, this is kind of exaggerated because, well, this is now 6 coupled quantum dots. That's today not possible. I think the world record is still with 3. But well, still, I mean, in theory, nobody, or it's still a good motivation to study it, even if it can be realized only in a few years from now. So what we are studying were always these type binding models, which means we have a lattice of discrete sites with various energies. The sites are tunnel coupled, and at the end, what we sometimes call the wire is coupled to Fermi seas at different chemical potential. And from chemistry, we borrowed these terms donor and acceptor, because if I remove the leads, then this is sometimes, or such models are sometimes used for the so-called electron transfer reaction. So there's a chemical reaction, there are electron tunnels from one end of a molecule to another end. And, well, finally, we have to model also the laser excitations. And this we do by classical fields. So what the field always does, it just varies the energy levels. So it acts as a classical dipole force. So the energy levels are actually shifted up and down. So this is the typical behavior of a system under a dipole force. And so this was the sort of basic setup or model that we always studied. Now my talk I will address actually these topics. Well, first I have to derive some theoretical description for such a setup. And what I will talk about today is mainly scattering theory. So we, in a sense, generalize scattering theory to the presence of time-dependent fields. And then come the main applications. How can we induce a DC current from an AC field? And that's the question all behind this ratchet field. And, well, with some special applications. Then a part that I actually skipped, but I still like to mention it because if there are questions, I have prepared some transparency. So those who are interested in Kohler blockade effects in this system, meaning when scattering theory does no longer work, what is beyond, then I can at least give in a private circle some answers. And finally, I will address a topic that we only studied recently. If I have a system that shows tunnel oscillations, can these tunnel oscillations be used as a driving force? Okay, but let's start with the theoretical description. So I suppose many of you are non-experts in the field of quantum transport, so I like to also introduce a bit to the field. And it possibly started almost or more than 50 years ago with the idea of Landauer, namely that conduction is nothing else but transmission of electrons from one end of a setup to the other end. So what we can do if the particles are independent, meaning if interaction doesn't play a significant role, we can compute the probability of an electron that starts here to be transmitted to the other end of the setup. We can do the same for the electrons below both Fermi surfaces, but this is actually, say, an irrelevant case because the electrons are scattered from the left to the right, and since at least in the presence of time dependence, time reversal symmetry, the forward scattering is equally probable to the backward scattering. The probability that an electron tunnels from the right to the left is just the same. So the net effect is 0. So only the levels or the electrons here in the so-called voltage window, meaning in the window between the the Fermi surfaces, they really give a contribution to the current, and all the others can be ignored, as well as those above, because if there's no electron, there will be no current. So, and here it's balanced, so finally only the electrons in the voltage window give a relevant contribution. Now, if one evaluates all these ideas and does all the numbers and the calculations, one finally finds the famous Landauer formula, which essentially represents the current as a function of the transmission probability at a certain energy, and which sometimes is modified also by the applied voltage because of electrostatic effects, times the occupation probability in the left and in the right lead, or the difference of the two. And then it's clear, if below both Fermi surfaces, both occupations are the same, they both are 1, then of course the contribution vanishes. So this difference of the Fermi function finally restricts the contribution to the voltage window. So the only thing that we have to finally compute is the transmission probability of an electron to go from the one side to the other side. And well, that relates the transmission probability to the Green's function of the electrons. And while Landauer has more or less conjectured that formula, later on it has been proven with model calculations by various groups. Now I also promised to talk a little about the shot noise properties of such a system. And Büttiger, almost 20 years ago, he generalized this Landauer formula to the description of the transport of the noise of the electrons. With the current that we finally get consists of flowing electrons, and of course that means that charges flow in discrete portions, and that of course gives finally some noisy behavior. And actually this noise is very well known. This has already been studied by Schottky with electron tube or vacuum tubes in the, I don't know, around 1910 or so, roughly 100 years ago. And now, evaluating these ideas for more modern setups, Büttiger found that the current correlation function, which is in the present context mainly evaluated at 0 frequencies, because the behavior for relatively low frequency is relatively flat. So mathematically it's for many situations sufficient to address the mathematical limit of the frequency going to 0. And what he found from this expression after a couple of lines of calculation was expression that reminds much to the Landauer formula. In particular, it is given by transmission probabilities and occupation numbers of the leads. The probability that a certain state is occupied or not. And the noise actually consists of two contributions. The first one is here sketched in blue. Obviously, this is, well, if we have finite temperature but 0 voltage, this contribution vanishes. For 0 voltage, well, the difference is just 0. And this can be interpreted as the shock, vice versa. If temperature is 0, this term still remains for finite voltage. And this is what can be interpreted according to Schottky as shot noise, meaning the noise stemming from discrete portions of the charge. The second part is equilibrium noise, because this even remains if the voltage vanishes. And of course, in a system at equilibrium, according to Carl and Melton, we must have some noise which is thermal noise, and that is expressed by this part. And the important thing here is that the noise only depends on the transmission probability. So quantum mechanical scattering phases do not count at all. They are, at least for this setup, not relevant. Now, what information does noise give us? Well, we have the Fano factor, which is always these noise strengths that I just introduced divided by the current itself. And this is a dimensionless measure and gives some information about the qualitative behavior of the system. And there are actually a few examples where this becomes evident. So suppose we have a double quantum dot, just as sketched before. So we have two leads with a voltage, and we have two wells in between. So we can consider actually this system in two limits. The first limit is where the barrier at the center is rather high and the outer barriers are very transparent. So in a sense, these outer barriers, they are we can forget about them. What now physically happens is that from the left, electrons are approaching the barrier and most of them are reflected. And as we all know from our elementary statistics courses, the transmission of an electron is now a rare event, and as we know from our courses, the statistics of rare event is Poissonian, which means that that the variance is equal to the mean of the number of electrons that is transmitted. And the Fano factor is actually defined such that for a Poisson process, it assumes the value of 1. Now, in the other limit, where the outer barriers are high and the central barrier is low, we have a slightly different situation. Because what now happens in the transport process, an electron will tunnel into the system, will stay there for a while, and only leave after some mean residence time. And while an electron is here in the system, it sort of blocks the transport. So the next electron has to wait until the electron that is already in the dot has left. And that means that finally the electron transport is more regular. And according to that, I mean here plotted as a graph as the Fano factor as a function of the tunneling here at the inner wall divided by the tunneling strength at the outer walls approaches a value of 1/2, which corresponds to the reduced noise due to that, say, more equal spacing of the electrons. And a quite interesting thing is that in the crossover regime, this behavior is non-monotonous, but it undergoes or it goes through a minimum. So if both tunneling rates are almost the same, one has the most regular transport, and according to that, to the Fano factor, the Fano factor assumes this minimum. Now, noise can be used as a signal, as already mentioned, and there is also another important case where this is visible. If we compare, at least for relatively small voltage, an ohmic resistor and a tunnel contact, then we find that in both cases, the voltage is proportional to the current. Well, the only difference is that here we have the ohmic resistor, while for the tunnel contact we have the so-called tunnel resistor. But the behavior, the linear dependence of voltage on current is not changed at all. But that's different for the noise. So for thermal noise, as already mentioned, we have some temperature-dependent contribution in the ohmic resistor, while for the tunnel contact, we have transport of individual charges. And then, as also discussed before, the noise is proportional to the current, and the proportionality constant is just a charge. So for a tunnel contact between two normal metals, this is just given by this expression, and the Fano factor will assume the value of 1. Actually, this is much less boring than one could guess, because if we have two superconductors contacted with a tunnel barrier, say a Josephson contact, then we have Cooper pair tunneling. So the transported charge is actually 2e, not only the electron charge. And then one can actually show, also experimentally, that the Fano factor assumes the value 2. And the even more recent and exciting application was done in close to Paris with the fractional quantum Hall systems, with the famous 1/3 charges. And that actually has been measured by noise measurements. So one can build a tunnel contact and finally will measure a Fano factor 1/3. Now coming a little to the theoretical description of time-dependent systems, one should maybe start, at least I'm going to do that, with the so-called Thiel-Gordon theory. That was actually the situation close to what I just addressed before. We have two superconductors and we have an insulating barrier in between. And the full line here shows the current voltage characteristics of that system. So we have, well, this is the typical behavior that is found for a gapped spectrum. I mean, this here corresponds to quasi particle excitations, and here we have tunnel currents. And there was an experiment in the 60s where people put such a setup into microwaves that finally lead to the famous Shapiro effect, which now is used for voltage standards. And what they found was, under the influence of microwaves, this tunnel system didn't show, or the current voltage characteristics of this tunnel system changed and acquired these steps with the size h bar omega divided by the elementary charge. And this experiment motivated Thiel and Gordon to make a sort of quite simple but intuitive approach to describe that theoretically. So what did they do? Well, I now formulate the Thiel and Gordon theory for normal conductor, because it's more relevant for the present case. What they just did was, well, they had such a situation, and the voltage they just modeled by shifting up and down the Fermi surface of one of the conductors. And so the voltage actually shifts the up and down the energies of the electrons in one of the leads. And in a quite heuristic approach, they just replaced the fact, this exponential oscillating factor that is well, quite characteristic for quantum systems. They replaced it by this modified energies, which are modified due to the applied voltage. And if one decomposes such an exponential, this exponential of a sine into a Fourier series, one gets Bessel functions as prefactors. In these Bessel functions, they have this characteristic dependence on the voltage that is applied on the amplitude divided by the frequency. And the interpretation of that expression was just that they now have some sideband contributions, which are occupied by according to the square of this, well, the occupation probability is the square of the amplitude. And so they just conjectured that the current in the presence of the AC voltage is just the current for an accordingly shifted voltage and weighted by these squares of the Bessel functions. And that actually described experiments quite well, surprisingly well, I must say. And later on, a couple of other physicists, they derived the according formula for the shot noise, and they found, well, essentially, well, a bit more complicated formula, but they also were able to decompose the shot noise in the presence of an AC field into contributions for the static situation. So what you just have to do, you have the static current voltage relation for various voltages. Voltage is changed by multiples of h bar omega, and then you weight it with this Bessel function and sum it up, and that's it. So a quite simple theory, although it's not, at least from what I told, not so clear when it holds. And actually, the theory by Thiel and Gordon, if you look at the paper, is nothing more than, say, putting these arguments a bit more into order, and but there's no true calculation behind. So that somehow brings me to the first questions that I'd like to address. Well, the derivation was heuristic, so is there a more rigorous derivation? And the second question, sort of a consequence of the first question, when is the Thiel and Gordon theory applicable? So when is life easy, if you wish? Now, if we address driven systems, then, well, the whole problem that, or what makes the theoretical study of these systems difficult is actually nothing else but this time ordering operator. So if we have time-dependent systems, we actually know it from perturbation theory in quantum mechanics. So once we have a time-dependent Hamiltonian, let it be an explicit time dependence coming from a field, or say an implicit time dependence due to the transformation to an interaction picture. In both cases, we have now to consider time ordering of this exponential. And all this looks in formal notation quite simple, but actually is quite some mess to really take that into account. But if we have periodic time dependence, we can get some ideas from solid state physics, because in solid state physics, people are calculating quantum mechanical wave functions in periodic potentials. So they also have a periodicity, but in the spatial degree of freedom. And what one can now do is one translates what is known as Bloch theory for solid state, for electrons in a solid state, in periodic potentials, to the time domain. And actually, if one goes to the literature, one will find that Floquet already developed these ideas way before solid state physics in the modern context was developed. So actually, it was vice versa. Bloch developed the ideas of Floquet and not vice versa. Although, say, for today's physicists, it's much easier to explain it the other way around. So what we're doing, we say make use of a mathematical theorem, which is called the Floquet theorem, and well, Floquet of course didn't formulate it for a quantum mechanical problem, obviously in 83, 200 in the 19th century. But say taking the mathematical statements of Floquet and applying it to the Schrödinger equation, one ends up with the statement that the Schrödinger equation with a periodic time dependence has a structure or a complete solution of the following structure. We have some exponential prefactor times some periodic function. And well, that sounds like shifting one problem or shifting the problems, because we started with a general time dependence and have now still a time dependence. But for numerical approaches, this is actually quite some achievement, because if you have an arbitrary time dependence, you have to really propagate the system, or if you a Fourier transform, you finally get a function, a continuous function of the frequency, while for a periodic function, you have only discrete frequencies, and that's, from a technical point of view, quite some achievement. And all the rest is essentially as we know it from solid state theory. We have, instead of quasi-momentum as in solid state, we have now quasi-energies, which is actually epsilon in the exponential factor. And we have a spectrum with a polymorphism structure, so essentially the same in the time domain as we know it in the spatial domain. And the whole, the whole procedure finally allows us to evaluate the response of a quantum system to an AC field to arbitrary order. So we really get an exact solution, at least numerically. Now, I have introduced you to transport theory, also the Floquet theory, and our goal was now to combine the two theories. So we have to develop a transport theory that is based on Floquet theory. And well, that's a lot of calculation. I only highlight some key points. If we have a transport situation, meaning we have a quantum system that is coupled to beads, then the main difference as compared to the closed system is the so-called self-energy. And this is the self-energy comes from the interaction of the central quantum system with a continuum. And finally, if we want to compute a complete set of solutions of such a system, we just have to augment the Schrödinger equation by the self-energy contribution. But of course, this equation, I mean, we don't solve this equation or we don't propagate it. This serves only for the purpose of deriving a complete basis. Of course, I mean, as a Schrödinger equation itself, this equation doesn't make much sense. I mean, Schrödinger equation is always coherent, so the self-energy doesn't make much sense. I mean, this is we're not solving our system with this equation. This is more a computational trick to compute the Green's function in the presence of the leads. And if we finally write down our propagator, we get something, a Green's function, which depends now not only on the time difference, but on the time difference tau, and also the absolute time. And that's a consequence of the time dependence of the system. And if one plays around with this expression a bit, then one finds actually a quite elegant expression. So the Green's function can be decomposed into objects like this here, this g of epsilon and k. Epsilon is a continuous energy variable, and k is discrete. And the interpretation of this Fourier components is that this describes the propagation of an electron with initial energy epsilon under the absorption or emission of k photons. So that not only gives some formal results, but also leaves room for interpretation. Now, one step further, we have to insert that into the expressions for the transport properties, here for the current, and we find this generalized expression for the Landauer formula. So we have transmissions from the left to the right and the right to the left, so the situation in general is now no longer symmetric, unlike in for static problems, because static problems, unless you have magnetic fields, they have time reversal symmetry. So forward and backward scattering is always the same, has at least the same probability. And this is now no longer the case, because a time-dependent field might break time reversal symmetry. So we have here these transmissions, which are just the squares of the Green's function, and we can write down the current formula of them. Well, that's a sketch of what happens. We have initial energies, we have absorption, we have emission, and we have the elastic channel, and also absorption and emission of higher order. And for the noise, we actually get a much more complicated expression. I don't discuss that in detail. The only thing that is relevant and interesting in the present context, that it is not, at least we didn't achieve to write it in a form which only depends on transmission probabilities. So one can actually conjecture that also the transmission amplitudes, especially the phases, are now relevant for the noise. And this is for two-terminal conductance something quite special to time-dependent systems. For static systems or for static two-terminal conductors, this is not so. Now we can also answer the question that motivated us in the beginning a little. When is T and Gordon theory applicable? So when is it possible to really write down the current voltage characteristics with a quite simple expression? And we found that this is possible if one just shifts up one chemical potential, or shifts up and down one chemical potential. And a special case of that are tunnel barriers, meaning the case studied by T and Gordon. So we really, our calculations really gave the result that the case studied by T and Gordon was certainly correct. Anything else would have been quite surprising. And it's also correct if we shift up and down the levels uniformly. So all levels are shifted up and down in the same way. And then of course, it's obvious that one can map this situation to the situation where both chemical potentials are shifted up and down. So it reduces in a sense to that one. But there is also a case which is quite important, in which T and Gordon theory is not applicable. And this is what I'm going to talk about in the following. This is the dipole force. So if we shift up and down the levels with a phase difference, like indicated here, then T and Gordon theory doesn't hold at all. So in that case, we really have to go back to our blockade theory, unfortunately. Now, discussing Ratchet effects. Well, the Ratchet effect, I suppose many of you already know, has originally been studied for Brownian motion. Brownian motion is the motion of classical particles in some spatial potential. And there is actually something that is, well, if you think for a while about it, not so obvious as it looks like. If you have an asymmetric potential and you have Brownian particles in it, then despite the asymmetry, you will not find any current. And the reason is actually a bit subtle. This is the kind of hidden symmetry called detailed balance. This would be a talk of its own, I just mentioned it. But the important thing is that in a static situation, the asymmetry doesn't lead to the creation of any current. But if you have asymmetry plus an AC force, detailed balance is violated. Well, the condition for it is no longer given. So we can really induce directed transport if we have spatial asymmetry plus AC driving. And that this idea actually is the sort of starting point for the Ratchet effect. And what we are doing here, we are sort of going to a new field, or we went to a new field of that Ratchet dynamics, which was coherent quantum dynamics with non-adiabatic driving. So something well, if you do it adiabatically, you can still map it to a static situation, but if it's not adiabatic, this is no longer possible. And, well, we want to see not classical Brownian motion, but coherent quantum dynamics. And the model in which we studied this is sketched here. So we have tight binding models with asymmetric groups, so we have kind of sawtooth-like potential profile. And there are, well, there's no voltage applied, certainly, otherwise, well, there would of course be current, so the Ratchet effect would be quite less interesting. So we have actually two questions now in mind. Well, first, how is the length dependence of the Ratchet current? So the main question was if, say, if for example dissipation is relevant for the Ratchet current, then dissipation in such a system is a kind of surface effect. So if I make the system longer and longer, it could quite well happen that the Ratchet current finally decays to zero, which is not the case, as we finally found out. And the second one is there any coherence left in the system? So which role does quantum coherence play for this system? And the answer to both questions can actually be given by two plots. The first one is, well, if we study the Ratchet current as a function of the number of asymmetric groups that we add, then we find that the current actually converges quite fast. Already if we have, say, between 5 and 10 of these asymmetric groups, the current will no longer change. So this is actually good news for those who do experiments. So in the former theories, people always studied infinitely extended systems. And then, well, in an experiment, the system will always be finite. So the question is how many or how often do I have to repeat these periodic units or these elementary units of the system in order to really get to what has been studied in the infinitely extended systems. And the answer is quite promising. 5 units should be almost sufficient. And the convergence goes to a non-zero bottom. This is also important. It survives. Well, the other thing is we find, as for the current as a function of the driving frequencies, we find really pronounced resonances. So this already gives a significant hint that quantum coherence plays a role. And we even find here the prime resonances, second order resonances, and also contribution of the higher resonances. And at least for the Ratchet experts, it's of course interesting. We also find current reversals. So the current is not only goes always to the same direction, but the direction really depends on details. And this is what in the literature is studied under the term current reversal, and we find it also here. Now, the system was, say, 10 or even, well, we studied up to 100 sites, is quite complicated. So a full qualitative understanding is not possible. So we try to study some more simple system. So we reduced it to sort of the minimum or the minimal system that shows these effects. And if one goes to the literature, one easily in the solid state context finds the paper by Brouwer, who studied something quite similar. What he actually had, he studied some potential constriction that connects a left Fermi sea and a right Fermi sea. So this is now the top view of the potential. And upon variation of the shape of the constriction, he found that under certain conditions one can actually induce a current, just like a Ratchet current. And the special thing that he considered was the adiabatic time evolution of the system. And he was able to relate the parameter variation. If he plots it, say, 2 parameters in parameter space, he found that he can relate the current to some properties of the conduction on this path that is, on which the parameters are changed. And he found actually a very special relation, and well, it relates to Murray phases and all these things. But one property of this result is that for each path or each cycle through the parameter space, a certain amount of charge is transported. So the current is proportional to the number, to the frequency with which you repeat this parameter variation. And then, of course, gives easily the idea that if I do it much faster, then the pump current will be much larger. But the problem, of course, is if I do it well too fast, then I will leave the adiabatic limit, and so the results of Brouwer will not hold anymore. So there arises naturally the question, what happens beyond the adiabatic limit? And in order to study that, we go back to this experiment from the Kauenhofen group that I mentioned before. They actually measured something quite similar. So this is here a small sketch, but I suppose it's visible. What they studied was the current in the absence of any transport voltage, but as a function of the internal bias of the system, the tuning. And what they found was that for one side of the detuning they found a negative current, for the other side of the detuning they found a positive current, so they really were able to observe current reversals. And the model that we now made was much in that spirit. We have an asymmetric level distribution, just two levels. We have Fermi seas without any voltage applied, and well, there's the usual excitation. And three questions that we had in mind was, how is the behavior close to resonances of the current and also of the noise? And how can it be that pumping and time reversal symmetry can go together? That's actually a question that comes to mind to the experts already quite soon. And here for the present setup, this is quite easy to explain, because there's a scattering process where an electron, here from the Fermi sea, enters the left level. It is promoted by the field and can leave the system to the right. Now there's the reversed process, which has the equal probability, but it's initially not occupied. So there's an electron transported from the left to the right, but not from the right to the left. So a net current actually survives. Now, we found some theoretical description for that system to get analytic results, and I skip it because of lack of time. I only want to discuss the behavior of the system. So here the first plot, the blue lines show the current, the red lines show the noise. And what was quite surprising to us was that when the current assumes a maximum, even the absolute value of the noise strength assumes a minimum. And that means that the Fano factor, which was the dimensionless measure for the noise strength, even assumes a more pronounced minimum. So the resonant transport of such a non-adiabatic electron or ratchet is has a relatively low noise strength. So that's actually quite good news for those who do experiments. And well, these black curves, they just mean that the theoretical treatment that I skipped is quite reliable, so both for the current and also for the noise. And again, well, we have the characteristic Bessel functions as usual, so the theory seems to work quite well. And then we can use our results to optimize the system, just to compare with the set parameters that the people in Delft had used for their measurements, and we find there's actually quite some room for improvement. So currents of 40 picoampere, which by now can be measured quite easily, should be possible. And the Fano factor is clearly sub-Bosonian, so it's a more regular transport than the usual transport through a barrier. Now, quite interesting is to compare our results with the adiabatic limit. And as I already mentioned, in the adiabatic limit we expect the current to be proportional to the frequency. But as I showed it with the sketch with parameter variation, the parameters have to go through a closed loop in parameter space. And since the current, the proportionality constant, relates to the area enclosed by these parameters, for the present setup, we just have one parameter that we vary. So we always go forth and back on the same line. And that means there's no enclosed area. So the adiabatic contribution to the current must vanish. So the natural guess is that the current should be proportional to omega squared for low frequencies. And well, then is the question, how about the noise? So we studied that, we studied the limit of low frequencies and found, as expected, the current proportional to omega squared. And then, well, the bad news, the noise is still proportional to omega. So in the low frequency regime, the transport will be noise dominated. So there will be huge noise and only a little current which might or might not be interesting. But say if one is only interested in a well-defined current, this is quite bad news. Okay, another topic that I want to cover briefly is what about not pumping electrons or charge, but heat. So this is the probably last topic that I will address today. Well, we first, for that purpose, have to define what we mean by heat. So if we consider the electron distribution or the occupation probability of a metallic heat, we have a Fermi function and we have a cavity potential. And heat, in that sense, is energy with respect to the many particle ground state of the system. So heat means we have excited electrons, hot electrons, and we have some holes below the Fermi surface. And if we want to pump heat, this is of course, say, creating heat is easy, but of course we want to do the opposite. We want to remove, to cool the system. And that means we have to somehow use these electrons here, the hot electrons, to fill the holes below the Fermi surface. And there was actually a similar idea by Kohler from Helsinki. He was actually somehow doing that with superconductors, so he tried to connect a normal conductor to a superconductor, and he managed to do it such that due to the appearance of a gap, which means there are no states available for the electrons, he was able to remove hot electrons so that he finally was able to cool down the system. And we tried to do that also with, or to propose something with AC fields to show that it's at least in principle possible to cool systems by applying AC field, which sounds like contradiction, but at least in theory it's possible. The experiments might be quite difficult. So what we had to do, we had to write down a balance equation for the energy, or for the energy of the transported electrons, and we essentially found that the energy or the heat of the, say, the right heat is dominated by these three scattering processes. So of course we have the elastic scattering, which doesn't change the energy at all. This removes hot electrons. Then there's the opposite process where places below the Fermi surface are filled, and there's also the scattering of hot electrons to states with lower energy. So this contributes to cooling. But of course there are always the opposite processes, and this of course contributes to heating, just the opposite. And there's now a problem if we have a time reversal symmetric system, which is we have these two, the reflection processes, they have the same probability, and since the lower states are always stronger populated than the higher states, we always have some net excitation. And that means, of course, that we always have heating due to the reflections. And the problem, or the question is now, can the scattering, the transmission processes, can they overcome the heating effects of the backscattering processes? And that's actually possible. And the setup that we studied is the one sketched here. So we have to use a double quantum dot, where we have to take two levels for each into account. And we have to manage it now such that the dominating scattering process will be the following. We start from a state which is occupied, very well below the Fermi surface. Then we need resonant tunneling, we need excitation of the electron to some place or to some energy close to the Fermi energy. So that process fills a hole. And we need a second process that removes a hot electron via a similar process to an empty place. And since now, for this process, the initial state is stronger occupied than the final state, we have some net energy transfer to the left, because we fill holes and we somehow remove hot electrons with that process. And we can compute now the numbers. We do some scattering theory for these potentials, and we find the the current as a function of the driving amplitude to have some maximum and also some minimum, but independent of the temperature of the attached leads. we always find points at which the current vanishes. And these are actually the interesting points, because if the current wouldn't vanish, we would charge the conductor, and that's of course what we do not want to do. We just want to cool it down without removing charges. And the energy balance actually at this point is, well, at least for relatively high temperatures, is negative. So we really can remove heat from one conductor just by applying AC fields. Of course, if one wants to do in real life the experiment, then one has to consider also heating effects in the bulk. But at least, say, theoretically it's possible, and yeah, of course we will never be able to compete with other cooling techniques, but to show that it's possible in principle is already some achievement. If we study this electron balance as a function of the temperature, we actually find that it's even possible to pump heat from cold to warm. And that's only possible if the temperature difference between the two reservoirs is not too big. So if both reservoirs are at the same temperature, the blue line, then of course it's relatively easy. That's already been shown in the plot on the slide before. And with increasing temperature difference, it becomes more difficult. So at least for temperatures above 1 Kelvin and temperature differences below, I mean absolute temperatures above 10 Kelvin and differences below 1 Kelvin, this should actually operate. And we can now compare that to the sort of idealized case where we cool one lead by attaching it to a lead at temperature 0. Then of course it's clear that this process that I just described somehow is spontaneous, because these electrons will leave and there will be holes that are filled. And this kind of optimum can be evaluated. So if we consider that this situation with an optimum transmission probability of 1 for independent of the energy, we find that the maximum cooling depends on the temperature squared, and we call this the quantum of cooling power. And well, if we compare now our results that we get for the realistic setup, we find that this is only about, say, the cooling power due to the AC fields is only about 2% of this optimal value. But of course, I mean, attaching to something with 0 Kelvin is only a Gedanken experiment that cannot be done in reality. Okay, so now I arrived at the point or at the chapter that I wanted to skip anyhow. If anybody is interested in how these effects now change when we take Coulomb interaction into account, well, I'm happy to discuss that after the talk. And the second part that I unfortunately also have to skip is, can we use tunnel oscillation as a driving source? And well, I at least sketched the main idea. So what we now consider is these two coupled circuits, and the first circuit is voltage biased. So what electrons can do, they can tunnel in, perform tunnel oscillations, and leave the system after a while. And these tunnel oscillations actually can be used as a driving force if we couple this conductor capacitively to another asymmetric conductor. And the interesting question is, of course, can that, I mean, of course, in theory it will work, but if I put realistic numbers, does it also work? And the main results are that we get currents, or this ratchet currents induced in that way, of the order of 0.1 picoampere, and that's something that is measurable today. So maybe it's roughly a factor 10 above what can be measured today. And well, there are some theoretical descriptions. So for those who are interested, I mean, there are some, for a master equation description, there are some peculiarities where one has to pay attention. And if somebody is interested in the technical aspects, I'm also happy to discuss that either today or tomorrow. And well, nice pictures, but I have to come to an end. So I introduced you to our Fouquet theory for driven conductors. Well, at least for a part, for the scattering part. You also have the master equation part, which I didn't talk about today. I discussed mainly these pump effects, and there are a couple of further effects that one can study. Of course, the most basic effect is this photoelastic tunneling, which has already been measured 10 years ago. And those who know my former boss, Peter Henke, they of course know that he studied by now quite quite known coherent destruction of tunneling. And of course, we wanted to see fingerprints of these effects also in our transport system, and we actually found that. Well, there's a question of how is disorder influencing these questions, and of course, dissipation is also a big issue. So in a realistic setup, the electrons couple also with the phonons of a substrate, and that leads to dissipation. And well, we have also studied that a little. And finally, I like to make some advertisement for our, well, not so recent review article. And well, thanks to people involved in these projects, and thanks for the attention.
Okay, thank you for the talk. There are so many results. So, yeah.
When you spoke about the time ordering, I think this is only when your Hamiltonian doesn't commute with itself at different times.
Right, but that's normally the case, because what you have is a spatial potential. So in a generic case, it's a potential depending on the position, and if one applies a dipole force, which means that you have a potential in addition which is always shaking like that, then of course this is proportional to the position coordinate. And it would of course commute with the static part of the potential, but not with the kinetic part, not with the tunneling terms. And that's finally the problem. And, well, I would say that in almost all setups where you have time-dependent fields that induce non-trivial effects, the static Hamiltonian doesn't commute with the priming. There may be a few exceptions, but generically it doesn't commute. No, it doesn't. It does for the infinitely extended type binding system. Occasionally it does, yes.
It's finite.
No, with finite for sure not, yes.
Okay. Yeah.
Could you put again this transparency of the 0 Kelvin lead in contact with a finite temperature of lead? I don't understand what is the flow of heat, and so you say this
one or
well, this one is the same, but I understand better the other one with the 0 Kelvin because with the next one. Yeah.
That one.
So what is the direction of flow of heat here?
That's pretty obvious. Well, at least
I understand that very classical. It seems that the right one will approach lower temperature, will cool. Right. But you say that the heat is flowing.
No.
The other one.
What is happening here is that well, this is obviously the hot lead, and that one is the one at 0 temperature. And what happens is that electrons that come from below the Fermi surface of the left lead, they will fill holes here. And since these states are less occupied than the corresponding states on the left, there will be a net flow from the left to the right of electrons.
Of what? Of electrons or of
electrons. But of course, since the system shouldn't be charged, we have to remove these electrons again. And that's done, well, also automatically, because we have here hot electrons, which go from the right to the left. So charge neutrality is granted. And the net effect will be that we fill holes and remove hot electrons. So the right lead is cooled down.
But when you say that you can have flow from cold to hot, is in this situation? Or
no, that's in the time-dependent situation.
Okay.
So what we compare with, we had before we had two leads where the left one was hot or hotter than the right one. So we had transport heat flow from cold to hot. And now we compare this situation with the idealized cooling. So cooling by attaching the right lead to something at 0 temperature. And of course, I mean, this is the most efficient process for cooling that you can have. But, well, in reality, we all know, I mean, if that
you don't have such.
Yeah, we don't have, well, we have it maybe, well, not even in the outer space, even there we have some finite temperature.
Okay, well, I have just a quick question. Well, actually, it's a remark. You said that the noise depends only on the transmission probabilities. But I think this is true only in the two-terminal case.
That's
right?
in the two-terminal
In
cases.
multi-terminal cases, you have
Right.
phases, right?
I mean, that's why I emphasized it, that it's special to the two-terminal case, that the noise depends now also on the scattering phases. For the 3 or 4 terminal, or say multi-terminal case, it's already a static situation like that.
Okay, so if there are no more questions, let's start the speaker again.
Coffee? Yeah, sure.